This congress you have organized. I'm very grateful with my tutor Alberto who introduced me to this wonderful set of ideas. And actually this is a joint work with him, and it is a sort of continuation of some earlier work by him and Adelic Nag in the 90s that I shall describe. But first of all, I'd like to take a couple of minutes to say why that work was important at that time. No, well, one of the main problems of string theory is that it lacks of an exact theory. We don't have an exact theory of string theory. It is defined as an asymptotic series. A result proved by Adelic Gross actually says that that series doesn't converge. And each of the terms of that asymptotic series is the one in here that one of the great things about it is that it is a finite dimensional integral over the finite dimensional moduli space of conformal structures of the Riemann surface of QG. And well, thinking in this direction, Hom and Rajiv, searching for an exact theory, actually said, well, if I am formulating each of these terms in the finite dimensional Teichmüllers, maybe I can have an exact theory in the universal Teichmüller space. And they proposed something like this: an integral over the universal Teichmüller space. Unfortunately, the expression they propose doesn't make any sense. It is a good try, but it doesn't work. It doesn't work even at the operational level. But these ideas led to a conjecture by them that this orbit, the group of orientation preserving isomorphism of the circle quotient by the rotations, would embed in the universal Teichmüller space in such a way that it contains all the finite dimensional Teichmüllers. And well, the answer was answered negatively by Nag and Verjovsky in the 90s with their embedding. But first of all, because we are looking for a generalization, for an Adelic generalization of the embedding, I'd like to describe precisely each one of the pieces involved in the embedding. The first piece is to study the quad-joint orbit of this group, thinking in the Kirillov quad-joint method. And well, the quad-joint orbits of this group are very simple. Are the group itself seen just as a manifold, and the group divided by the quotient by rotations, it's interesting to notice that by general theory, this grouping here, this manifold is symplectic, and well, this other manifold is symplectic too. Actually, is a Keller manifold with this symplectic form and complex structure. The Virasoro quad-joined orbits are much more interesting. And are the one in here. Again, by general theory, they are all symplectic manifolds, but the only one that are Keller manifolds are for the case key equals 0 and 1. And it's interesting to notice that in the case key equals 0, we have the same orbit as the one before, but with another symplectic form. They are diffeomorphic, but not simplexomorphic. And well, if we consider the quasi-symmetric model of the universal Teichmüller space, this is the quasi-symmetric maps of the circle coefficiented by the Möbius group, PSL2R. And because every diffeomorphism is a quasi-symmetric map, we have by the composing with the canonical inclusion, we have this embedding here. And if we consider what I said before, the Keller structure of the left-hand side and the Weil-Peterson metric in here, it results in a beautiful result that the embedding is actually isometric analytic. So we can see the Virasoro orbit as a complex submanifold of the universal Teichmüller space with the induced metric. And well, several remarks. Acting with right translations of the universal Teichmüller space, we actually have a foliation of the universal Teichmüller space by Keller leaves. The other remark that is important too is that, well, because the Teichmüller space is a covering space, the covering of the moduli, we need a reference point, a distinguished point to make that covering. And every structure I have in the Teichmüller space, at the end of the day, I have to prove that they are base point independent. For example, the complex structure, at the end of the day, if I define it in the Teichmüller space, I must prove that it is base point independent. Well, with the Nag-Verjovsky embedding, this is automatic. I can define the complex structure without proving anything else. Well, and because of this other property here, that the Teichmüller, each finite dimensional Teichmüller is actually transversal to that embedding, this is definitely a negative answer to the Rajiv conjecture that they were wondering if each finite dimensional Teichmüller was contained in the embedding. And I want to say just maybe I comment at the end of the talk that this actually proves that our work is transversal to the one of Dennis Sullivan, for example. Dennis Sullivan studied the Teichmüller space of the universal hyperbolic solenoid. And because of this property here, our work is literally transversal to the one of Sullivan. So we will get new results, new conditions. It's a whole different theory. So we wonder, can we generalize this embedding if we, instead of considering the circle, we consider the adelic solenoid? That's the main point of this talk. We should generalize we should get an appropriate notion of or an adelic version of the Teichmüller space and generalize all the pieces of I just described of embedding. Well, the adelic solenoid is just the inverse limit of these finite coverings. I am making a deep abuse of notation in here that is denoting by S1 what actually is the unitary group U1. They are very different. This is just a manifold with no distinguished points, and the group has a group structure with the unit as a distinguished element. But this is the abuse of notation I will make in the whole talk. And if I consider the subgroup of the unit and consider all the respective kernels of the covering, these are group morphisms. I see that actually the profinite completion of the integers, the adelic profinite completion of the integers, is a normal subgroup of the solenoid. We will think about the solenoid in three different ways. The one is the one I just mentioned, that is considered the solenoid as a compact abelian topological group with the completion of the integers as a normal subgroup. The other one is the geometrical one. It is to see it as a pure bundle over S1 with monodromy the shift. And the third one is to see it as a dynamical suspension of the shift. You can imagine here the circle S1 down here and the solenoid fibering over the circle with the Cantor set as a fiber. And in order to construct an adelic version of the Nag-Verjovsky embedding, we have to construct an appropriate Virasoro algebra, calculate the respective Virasoro orbit, and define an appropriate Teichmüller space. So for the first item, we have this theorem here that says that the Virasoro algebra, the right Virasoro algebra, is just the inductive limit of all the Virasoro algebra at each level of the inverse limit. And explicitly is this algebra here. Two remarkable things: the appropriate central extensions, the one with the cube there, and the generators are indexed in the rational numbers. That's the reason of that is essentially because the Pontryagin dual of the solenoid are the rational numbers. the only, among all the Virasoro orbits of this group, the only one that is actually Keller is this one. There should be no pattern there. With this selected form and this complex structure. And well, it only remains to discuss the third point, the third item, that is to construct an appropriate diameter space. And the keystone of the problem, the heart of the problem, is in the Alford-Squares theory, is Alford-Squares theorem that says, consider a Beltrami coefficient in the unit ball of L infinity. Then there is a unique quasi-conformal mapping fixing the poles and a point in the equator, such that the Beltrami equation is satisfied in the weight sense, in the distributional sense. In the same way we have constructed the Adelic solenoid, we construct what we call the Adelic Riemann sphere, and what I call the algebraic solenoid. It's a inverse limit of branch, inverse limit of coverings of the punctured plane. Well, because the completion of the integers is a totally disconnected space, actually the P1, the projection to the first factor, is a local homomorphism, so I can pull back the whole differential and complex structure of C to the algebraic solenoid. To get a geometrical picture of this algebraic solenoid, the algebraic solenoid is foliated by leaves that are dense immersions of the complex plane. This is the principal base leaf, and well, it is natural to think that if the algebraic solenoid is foliated by essentially complex planes, and I have a very well-established theory of how to deform the complex structures of complex plane, that is classical Teichmüller theory, then it is natural to think that doing a deformation leaf by leaf would lead us to our notion of Teichmüller space for the solenoid. But this approach fails for two major reasons. The first one is the fixed point problem. The Adelic Riemann sphere, the topological nature of its poles is very different from all the other points in there. The poles of the Adelic Riemann sphere are actually cusps. So while in the classical theory the points 0, 1, and infinity that remain fixed was just a choice. I can choose whatever 3 points I'd like. In our theory, it is a constraint. I cannot longer choose them. The poles have to be fixed or permuted by them, but it is not longer a choice. It is a constraint of a theory, and there is no way of fixing 3 points of the leaf in such a way that the poles remain fixed. So this is the first problem. But the major problem is the second one. Even solving the first problem, there is no way a priori that I can guarantee that a quasi-conformal solution in each leaf would be, of course it will be horizontal continuous, but I cannot guarantee that it will be transversal continuous. Thinking in the fiber bundle way, that I have an horizontal structure and a vertical structure. And I write in here, it's like drawing a picture in each piece of a puzzle and expect that after we put all the pieces together, we get a clear and nice picture. We only can assure that if we have a structural condition, a global structural condition. So let's find out what the condition is. This is an example of the phenomenon I just described. This counterexample is called Alberto's nightmare. And well, the way we solve it is considering, the way we solve it is to think of a solenoid in this way. The way of solving the problem is to think of the solenoid in each of its approximations, and to give conditions of that are sure that the solutions converge to a solution of our problem. That's the main idea. So we introduced the nth renormalization maps, that is essentially averaging the Beltrami coefficients. From now on, we will assume that if we consider a mu in L infinity, we are saying that it is horizontally in L infinity and vertically in L infinity. To assure that these new Beltrami coefficients that live in the respective n level of the inverse system, to assure that they converge to the original mu, we need the notion of L infinity continuity. There's the one here. We say that it is L infinity transversal continuous if this condition is verified. I briefly describe it. We have the natural left action of the normal subgroup in the solenoid, and this gives us a right action on L infinity of the solenoid in this way. And if this map is continuous, because essentially this composition in here is translating the Beltrami coefficient vertically. It's translating it along the fibers. And well, if mu is transversal continuous, then the nth approximations converge uniformly to mu. In this way, we have now we have hope that solving the problem for each level could take us to a solution of the mu. And we still need to find out what the structural condition is, the one that is said before. That condition is the convergence of this series. This is the structural condition that we were looking for. The one that assured us that after we put all the pieces together of the puzzle, we get a clear picture. And well, if we have a transversal continuous mu in Beltrami coefficient in L infinity, and we can find a totally ordered cofinal subsystem of the divisibility system in such a way that this series converge, then we have a quasi-conformal map in the Adelic solenoid. There are some comments I'd like to say here. The main difficulty here is that we don't have a Fourier theory in L infinity. Fourier theory lives in L2. So we can interpret this different as Fourier modes in some sense. That's the idea. What is really interesting are these renormalization factors in here. That was very unexpected. And from this point, it is up to technicalities. It is straightforward to generalize it's straightforward to complete the Alford-Verse theory. In this context, we define the Teichmüller space, we construct the quasi-symmetric model of it, and then we have the Adelic Nag-Verjovsky embedding. But the heart of the problem was Alford's Verse theorem in this context. Well, that's it. Thank you very much.
Any questions?
Well, as you explained, this tabular space is covering a modular space. This infinite dimensional tabular space we obtain as covering of something.
Well, I'd say no, because what is the analog of what is the Adelic version of a Riemann surface? Well, it could be the Sullivan's hyperbolic solenoid. And as we said before, our theory is transversal to Sullivan's theory. And well, I said it doesn't correspond to a primitive object.
Any other questions?
Is there a map to that? It's the same question as earlier. There's no natural motion map in that.
Yes, no. If we don't have a primitive object to see this Teichmüller space as a covering of this proof, we don't have a map.
Any other questions? Well, thank you very much.
Thank you.